Let's do another example now. So in this example, we have a dust particle. It has a mass of 5 times 10 to the minus 9 kilograms and a charge of QO equals 2 nanocoulombs. So our dust particle is going to be charged QO. It starts from rest at point A and it moves in a straight line to point B. And we're asking, what is its speed when it gets right here? And we see that our charge is in the vicinity of two other charges. I'm going to call the 3 nanocoulomb charge Q1 and the negative 3 nanocoulomb charge Q2. So if we're moving from here to here, it's moving in an area with charges. There's going to be potential and potential energy. This is going to be a conservation of energy problem if you want to find the speed. We wouldn't be able to use kinematics because as it moves, it's a different distance from the charges, so there's different forces and acceleration varies, so we have to use an energy strategy here. So our final mechanical energy is our initial plus work done by non-conservative forces. That bit's going to be 0, there's no friction or anything. My final is when it gets to B, so EB. My initial is when it's at A equals EA. And my two kinds of energy are kinetic and potential. Okay, first off the bat, we're releasing it from rest, so the initial kinetic energy is 0. The speed at A is 0, so Ka, a half mv squared, is also equal to 0. My kinetic energy at B then is going to be UA, subtract UB. My kinetic energy at B is going to be 1/2 times m times VB squared. I know my m, I want my V, so now I need to deal with my energies. Let's think about how I'm going to get my energies. So I know that potential energy is charge times potential. That means if I want my potential energies, I have to sort out my potentials. Let's do that bit next. So my potential at point A VA is the potential of charge 1 at A plus the potential of charge 2 at A. K times Q1 over R1A plus K times Q2 over R2A. R1A is the distance between charge 1 and point A. And R2A is between charge 2 and point A. And I'll just put that distance up here where it's nice and big. We can see those numbers in our diagram. This distance is 1 centimeter, this distance is 2 centimeters, so let's do this calculation. We've got K outside of Q1, that's 3 times 10 to the minus 9 coulombs, divided by R1A, 0.01 meters, plus Q2, which is minus 3 times 10 to the minus 9 coulombs, divided by, and remember potential depends on charge, it can be positive or negative, divided by this distance, R2A, which we see is 0.02 meters or 2 centimeters. That gives us a potential of positive 1,349 volts. We also want our potential at point B. VB is the potential due to charge 1 at B plus the potential due to charge 2 at B. K times Q1 over R1B plus K times Q2 over R2B. Let's see what those distances are. When we're at point B, R1B is between R1 and B, and R2B is between Q2 and B. So we've got K outside of Q1, that's our positive 3 nanocoulombs, divided by R1B, that one is 2 centimeters, plus Q2, that one is minus 3 nanocoulombs, divided by R2B, that's 1 centimeter. Put that through the calculator, we should get minus 1,349 volts. So there are my potentials, VA and VB. Let's clarify what we mean by all the other points. So we said that Ka was 1/2 times m times VA squared, but our VA was 0, so that was 0. KB is 1/2 times m times VB squared. Here we might remember that m is 5 times 10 to the minus 9 kilograms. UB equals QO, times VB. I'll try and be really clear on my differences between my V's here. We can go ahead and do the numbers here if we wish. So QO was 2 nanocoulombs. Multiplying by VB, minus 1349 volts, to get a potential energy of minus 2.697 times 10 to the minus 6 joules. And my potential UA is QO times VA. We can put in our numbers here as well. So our 2 nanocoulombs times positive 1349 volts to get positive 2.697 times 10 to the minus 6 joules. Okay, now we have something for every symbol in our equation. So UA minus UB is going to be 2.697 times 10 to the minus 6 joules minus a minus 2.697 times 10 to the minus 6 joules. So then VB is going to be this difference times 2 divided by the mass. Take the square root to get the speed, and we get 46.4 meters per second. I guess that's going pretty fast for a little dust particle. Okay, why don't we work through one more example here. And this is going to take us back to an electric field example we've done in the past. So I think we can review through this one pretty quickly, or half of it pretty quickly anyway. So our question is, if I place 2 charges on the horizontal, I'm going to put plus Q here and minus 2Q here. 2 questions. Where is the electric field 0 and where is the electric potential 0? So let's do the electric field first, and we'll do it pretty quick just for a reminder. For the electric field to be 0, it meant that the electric fields had to be equal and opposite. So the net electric field equals E1 plus E2 equals 0 means E1 and E2 have to be equal and opposite. If we picked a point here in the middle, E1 would point this way, E2 would point this way, so we can call our charge, this one is charge 1, this one is charge 2. So they can't be opposite directions here, so this is not where it's 0. If we were out here, our electric field due to charge 1 is very small, points away. Our electric field due to charge 2 is very big, points in, because we're close to a big charge. So here, while they can be opposite in direction, they can't be equal in magnitude. That means that the electric field has to be 0 out here. At this point, the electric field points away from charge 1. We're close to a small charge. We get about a medium field. The electric field points in towards charge 2. We're far from a big charge. We get about a medium field. So this is the region where it's 0. To get equal magnitudes, we know that the magnitude of E1 is equal to the magnitude of E2. So K times the magnitude of Q1 over R1 squared equals K times the magnitude of Q2 over R2 squared. Put our distances in our picture. R1 is from here to here. R2 is from here to here. You might notice that R2 equals R1 plus D. So this plus this gives us this. We can cancel our K's. Q1 has a magnitude of Q. That's divided by R1 squared. Q2 has a magnitude of 2Q. That's over R2 squared, but R2 is R1 plus D squared. Those Q's cancel. Take the square root of the top and bottom. We get 1 over R1 equals root 2 over R1 plus D. Do some cross multiplying. R1 plus D equals root 2 R1. R1 equals D over root 2 minus 1, which is about 2.41 D to the left of charge Q1. So that's where the electric field is equal to 0. So the net electric field equals 0 at 2.41 D left of Q1. Okay, what about the electric potential? So this is a different question. Where is the electric potential equal to 0? when we were doing the electric field, you notice that the first thing we had to do was think about the direction of the vectors, and we said they had to be equal and opposite. Electric potential is different. Electric potential does not have a direction. In order to get our net electric potential to be equal to 0, they just have to have opposite signs, and they have to have the same magnitudes. Okay, so the direction, there is no direction, so we can't think about directions. So the way to get an electric potential equal to 0 is we have to be a little closer to this one than we are to this one. That's basically the only requirement. So I can think of two places we can have that. Two choices for our electric potential. Choice 1 might be right here. So if I'm out right here at point P1, let's see if this matches. So I want my net electric potential, sum of my V's equals V1 plus V2 equals 0. V1 is always going to be positive because my charge is positive. V2 is always going to be negative because my charge is always going to be negative. So in theory, I could have a point out here to the left of Q1 where my potential is going to be 0. I'm going to try and figure out if that's true. So at P1, my net potential at P1 is V1 plus V2 equals K times Q1 over R1. So my R1 is from here to here, plus K times Q2 over R2. My R2 is from, R2 is from here to here. R2 equals R1 plus D. So far we're following pretty closely to what we did for our electric field, and we want that to be equal to 0. So that says K times Q1, K times Q1, which is plus Q, divided by R1, plus K times Q2, which is minus 2Q, divided by R2, where R2 is R1 plus D, has to be equal to 0. First thing I can do is divide both sides by K and both sides by Q. So I get 1 over R1 minus 2 over R1 plus D equals 0. Now, I can definitely solve this for R1. 1 over R1 equals 2 over R1 plus D. R1 plus D equals 2R1. So R1 equals D. So our electric potential will be 0 at a distance D to the left of Q1. So net potential equals 0 at D left of Q1. Okay, definitely true. But I think there can be another spot, and I think there can be another spot in right here. So let's look at this spot. We'll call this spot P2. So at P2, my total potential at P2 is V1 plus V2. I want my total potential to be 0 equals K times Q1 over R1. When we're at P2, my R1 is from here to here, plus V2, K times Q2 over R2. R2 is from here to here. And we might notice now that R2 is equal to D, take away R1. So 0 equals K times Q over R1 plus K times minus 2Q over D minus R1. So to get R2, we start with D, and then we take away R1, we're left with R2. See that my K's cancel, my Q's cancel, and now I've got 0 equals 1 over R1 minus 2 over D minus R1, so I can definitely solve this for R1. 2 over D minus R1 equals 1 over R1. 2R1 equals D minus R1. R1 equals D over 3. So my net potential equals 0 at D over 3 right of Q1. I wouldn't get a potential close to minus 2Q because that charge is just too big and we're too close, so you would never get them to be equal. So you have to be closer to the small charge to get them to be equal. So here's a difference between field and potential. The electric field is only zeroed at one spot, but the potential could be zero at both spots, and that comes from the fact that our potential is our scalar, but our field is a vector.